Hello and welcome to video 4 of the FP3 chapter Matrices. On the screen is a very long starter question. If you've got time, pause the video and give this a go. But I will not go through it in this video. What I'm going to do instead is show you the mark scheme. You can see here you get a mark for getting the determinant of M correct. You then get a mark for starting the process that we did in the previous video. It would be the matrix of minors that you do first. Then you get a method mark for having a full process to get to something that looks like this, including this bit. An answer mark for getting it mostly correct, and a second answer mark for getting it fully correct. In this video, we're going to use matrices to represent linear transformations in 3 dimensions. And at the end of the video, we will also tag on this one here, because after you've done this, this is quite quick to look at. So you've done something like this in FP1. A linear transformation can be represented by a matrix. And previously, the linear transformation definition is that it always maps the origin onto itself. A more formal definition is a transformation where these two statements apply. That is, enlarging the vector by a scalar does not matter if it happens before or after the transformation, and adding two vectors, then transforming them gives the same as transforming them and then adding them. And that has the same effect as this. Specifically, enlargement about the origin, rotation about the origin, and reflection along a line that goes through the origin follow these rules. But no matter what limitation you put on translation, you cannot get it to follow these rules. Any translation will not map the origin onto itself. And you might see this. This is telling you the transformation is mapping 3-dimensional space onto 3-dimensional space. A point after being transformed is known as the image. The last thing you need to remember is that the transformation T, in bold here, and the transformation U, in bold here, these bold ones are the matrices representing those transformations. If you want to do UT, that means the transformation T first happens, and then the transformation U happens afterwards. So remember, when you apply this to a matrix, it's the one on the right that happens first. Okay, that's enough to get us started. First thing, linear transformation. In FP1, you learned that if you know the transformation effect on the vector xy, then you can use that to find the matrix to represent that transformation just by taking the coefficients out and making the matrix with them. And that comes from the logical idea of, I know that if I multiply this by this, I get this. Therefore, if the transformation has this form, I can infer that A, B, C, and D from here was the matrix it came from. And we can do the same thing in 3 dimensions. So if you have a transformation and you've got the vector effect of what happens to that xyz vector after the transformation, you can use the coefficients to create your 3x3 matrix that had that transformative effect. Simple example then, determine the matrices representing these transformations. So the matrix T, taking the coefficients of x, y, and z, 1, 0, 1, and the coefficients of x, y, z on the second element, 0, 1, 0, and the coefficients of x, y, z on the third element, 1, 2, 1. And you can see that the coefficients here have just been used to make the matrix. And that's because I know if I apply this on x, y, z, we know how matrix multiplication works, and we know that this multiplication will give us this answer. Same thing for U. Get 1, minus 1, 1, 3, 0, minus 2, 3, minus 4, minus 1. So this is a very simple idea. Hence, find the matrix representing T followed by U. If you want to apply these matrices to the matrix M, T first, followed by U. So the multiplication U times T will give me that answer. Which gives us 1, 0, 1, that's a 2. 0, minus 1, 2, that's a 1. 1, 0, 1, that's a 2. Then we have 3, 0, minus 2, gives us a 1. 0, 0, minus 4. 3, 0, minus 2. 3, 0, minus 1. 0, minus 4, minus 2. 3, 0, minus 1. And that is our answer for that. Second example. Transformation T transforms 3D space to 3D space using the matrix bold T. The point with position vector this is transformed to this. So T is having the effect of changing this vector into this vector. Similarly, T is changing this vector into this vector, and this vector into this vector. Find T. Now it's quite important here, the numbers they've given us involve a certain amount of zeros, because we're going to apply this step by step. And we're going to have a general matrix A, B, C, D, F, G, H, I. And I'm going to apply this on my first position vector that I know is transformed into 3, 4, 2. And this approach would be far more difficult if we didn't have all these zeros here. But what we can say here is A times 1, B times 0, C times 0 gives me 3. So A must be 3. Similarly, D times 1, 0, 0 gives me 4, so D must be 4. G times 1, 0, 0 is 2, so G must be 2. In other words, 1, 0, 0 is giving me the first column of my matrix here. So I can say 3, 4, 2, B, C, E, F, H, I, and I can apply this slightly more known transformation to this one, which has a 0 down here. 1, 1, 0, and I know that transforms to 6, 1, 5. And I'm going to do the same thing again, because now we've got our first column. This is going to help us get the second column, because this 0 here means each of these is going to disappear. So 3 plus B plus 0 is 6, so B must also be 3. 4 plus E plus 0 is 1, so E must be minus 3. And then the last one, 2 plus H must equal 5, so H is also 3. You can probably see where we're going here. This is now enough information that our final point, transforming this to this, will give us the final 3 values. So we've got 3, 3, C, 4 minus 3, F, 2, 3, I, applied to the point 2, 1, minus 4, must transform that point 2, 1, 1, minus 1, and that's enough to make simultaneous equations. So we've got 6, 9, 9 minus 4c must equal 1. 4c is 8, c must be 2. Then we keep going. We've got 8 minus 3 is 5, something to give me 1. That's our second row. So we've got f must be 1. The last one, 4 plus 3 minus 4i. Must equal minus 1. So our final answer of the matrix T is 3, 3, 2, 4 minus 3, 1, 2, 3, 2. Then we need to find the image of the point with position vector minus 1, 3, 0. I'm running out of space, but I don't really want to delete that. So let me squeeze it in here in green. And we're applying that to minus 1, 3, 0. And then this is the easy part, applying the matrix transformation that we know to a position vector that we know, we simply do the multiplication. So we've got minus 3 plus 9 plus 0. Minus 4 minus 9 plus 0. Minus 2 plus 9 plus 0. So the answer to part B is the vector 6 minus 13, 7. That is enough for you to practice questions 1, 2 and 3 from exercise 6D. And if you want to break now, this is a good point to stop and try those because the next few examples are quite long. So to transform a point, we do just what we did in the previous example. We apply the matrix to the position vector of the point. That's what we did here. And you can use that same idea for a line and for a plane, so long as you have the general point of the line or the plane. So if you've got the general point, you can simply apply the matrix to the general point, and that will give you the transformed general point, which you may or may not have to put into a different form depending on what the question asks you to do. So this is a fairly simple method, although not all the questions will be simple. And you'll usually find that lines map to lines and planes map to planes, but that's not always the case, and we will look at an example where that does not happen. The example we look at will have a plane mapping to a line, losing a dimension, and you can't go backwards from that. There's no way to transform the line back to a plane. You would not have enough information. And the question in blue here, what type of matrix might do this? The answer is a singular matrix, a matrix that does not have an inverse. Okay, our first question. The transformation T maps 3D space to 3D space represented by bold T matrix, which is this. So we're told the transformation. The plane pi1 is transformed by T to the plane pi2. The plane pi1 has vector equation this. Find a vector equation of pi2. So what this question is asking us to do is to apply this transformation to this plane to find the new plane, the transformed plane. So we just do it. We apply this matrix to this. But we can't do it as it's written here. We need to make this into a general point. And to do that, we just add these three together. So 2 plus 1 times s plus minus 3 times t. And that's the parametric form of my x of the general point x, y, z. For y, we've got 1 minus 2s plus t. And the parametric form of z, minus 3 plus 3s minus t. Now, although there are lots of bits to this, there are only 3 elements, x, y, and z. And I can apply my transformation t to this vector. To save space, I'll just write it here next to t. So we've got 2 plus s minus 3t, 1 minus 2s plus t, and minus 3 plus 3s minus t. And then we go ahead and do the multiplication. So we've got 2 lots of this, plus 5 lots of this, minus 1 lot of this. So although it's a fairly simple thing to do, it's not necessarily a quick thing to do. We've got 4 plus 2s minus 6t, and then 5 times the second element of the vector, 5 minus 10s plus 5t, and minus 1 times the third element of the vector, plus 3 minus 3s plus t. Then we have the second row times each of these. Fortunately, we've got a 0 here, and we've got a 0 on the third one as well. That will speed it up a little bit. So we get minus 12 minus 6s plus 18t plus 0 times the middle one, minus 6 plus 6s minus 2t. And then the third one, we've got 0 times this, 4 times this, and 3 times this. So we have 4 minus 8s plus 4t minus 9 plus 9s minus 3t. And that, if we simplify it, becomes 12 minus 11s plus 0t. I'll write it like that for a second. Minus 18 plus 0s plus 16t minus 5 plus s plus t. And that is the general point of plane 2. Vector equation of plane 2, we can change the form here by doing this process backwards, so we can split off our 3 parts to get r is equal to 12 minus 18 minus 5 plus s times minus 11, 0, 1 plus t times 0, 16, 1. So a quick recap of what we did. We put this into a general point so that we could apply the matrix T. The long process of doing that to get the answer, the transformed point, simplify that up, and then split it into the required form. This example is a little bit more complicated. The transformation T from 3D space to 3D space is represented by the matrix bold T here. Plane pi has equation this. Show that the image of pi under the transformation T is a line, and find the Cartesian equation of this line. The first difference is that we don't have an easy way to write the general point of our plane. To get a general point from this equation, we need to do something a little bit sneaky. Recall that this means this. where this vector here is the normal, and this is a dot n. So one thing we could do is to take that normal and find a vector, any vector, that gives me the dot product equal to 0. And we can make it really easy. We can say, let's make that a 1, so that gives me 2 times 1. Make this a 2, so that gives me a minus 2, so 2 minus 2 is 0, so I put a 0 there. And this vector, dot this vector gives me 0, tells me that this is perpendicular to this. Therefore, it is parallel to the plane. So this is one equation parallel to the plane. And then I can do the same thing with any other different vector. So let's say, make that a 0, and then a 3 and a 1 here, because I know that will give me a dot product of 0 as well. So here I've got two vectors that are both perpendicular to the normal, and therefore are parallel to the plane. So I can write my plane equation, r is equal to some point plus s times the first one here, plus t times the second one here. And then all I need to do is find a point, and I can find a point by putting any x, y, z into this equation and satisfying the dot product equals minus 6. So let's say 2 minus 1, 3. To get minus 6 out of this, what I could do is put a minus 3 here, and then a 0 and a 0. And that will give me minus 6 as required. So this is a point on the plane. Then I've got a general equation of the plane, and I can follow through like I did in the previous example. However, that's quite a lot of work, and in this case, there is an easier way. What we can do instead is to let one of these variables, say x, equal the parameter s, another one equal the parameter t, and then rearrange for the third one in terms of the first two. So in this case, it's quite easy to make y the subject, so we'll do that. And I can make x parameter s, z parameter t, and then y becomes 2s plus 3t plus 6. So my general point will be this. And that cuts out a lot of the work to get it the other way. And you might notice that this gives us a slightly different general point, but if you were to follow through both methods, at the end you would get the same answer. I'm going to follow through with this one because it's just going to be a little bit easier having an s and a t and nothing else in these two elements. So now we need to do what we did before, multiply our matrix by our vector, get the transformed general point, and then we need to show that that is a line and put it into the Cartesian equation form. So again, this might take a little bit of time. 2 times s minus 1 times this plus 3 times this. So we get 2s minus 2s minus 3t minus 6 plus 3t. Then we have minus s plus 8s plus 12t plus 24 minus 2t. And the third one, 3s plus 4s plus 6t plus 12 plus 4t. I'm going to simplify that down here. So this is not t anymore, this is t applied to the general point, and we get the 2s's cancel out, the 3t's cancel out, and we just have minus 6. For the second element, we have 7s plus 10t plus 24, and for the last one, 7s again plus 10t again plus 12. So this is the transformed general point. And to show that this is a line, you can do two different things. You can look at it logically, and you can say this is that general point x, y, z, transformed, of course. And what that's telling us is that x equals minus 6. And that is an absolute statement. X does not change, it is just minus 6. That by itself tells you that the rest of the movement of the line as s and t change happens in this plane x equals minus 6. The yz plane that goes through minus 6 on the x-axis. But we also need some connection between y and z to get that line equation. To do that, I note that y is equal to 7s plus 10t plus 24, and z is equal to 7s plus 10t plus 12. And this is a nice question because I can relate these now simply by subtracting one from the other, and I get 12. So y is equal to z plus 12. And within the plane x equals minus 6, this is the equation of the line. And arguably, you could stop there and say this is clearly a line. However, this question is a little bit strange in that it wants you to find the Cartesian equation of this line. And that is quite a weird looking equation. At the moment, it's not too bad. I can make this equal to lambda, and you know that that's close to the Cartesian equation of the line, especially if I change that y into a y minus 0 over 1, and I can put an over 1 here with this. But I don't have an x statement here, and that's because x is simply equal to minus 6. And I would suggest, personally, that this would be enough, leaving this separate to this. But what you'll see in the textbook as they go through this example is they add this on with the justification that you can write x plus 6 equals 0 times lambda here. You can write this as x plus 6 over 0. And I guess insofar as these numbers here represent the position vector of a point and these numbers here represent the direction vector, yes, that's okay, I guess. But I think you can see why I'm not happy with this, that dividing by 0 there, unless you weren't going to leave it there and were going to do the next step of writing it in vector form, I wouldn't do that myself. But they do that in the textbook, and that's where it's come from. And that is the end of this example. That should be enough for you to practice these questions from exercise 6D. But a quick tag on the end here, this one, using inverse matrices to reverse the effect of a linear transformation, the whole idea of that basically is what it says right there. You can reverse the effect of a transformation by using the inverse matrix associated with that transformation. So if we do a transformation T, then we can go back by using the inverse matrix T minus 1. However, you know and I know that getting the inverse matrix is quite a long process. So if the question doesn't say that you have to find the inverse matrix, it might be easier just to use simultaneous equations. Now let's be clear, if the question says by finding the inverse matrix, or if it tells you you must use the inverse matrix in some way in this question, then that's what you've got to do. But if it doesn't, then there is an easier way. So here is an example where the textbook uses an inverse matrix to answer this, but I'm not going to. I'm going to use simultaneous equations. And sometimes this will be easier than others. Here, because we've got a number of zeros in this matrix, it's actually quite straightforward, and certainly saves a lot of time as compared to finding the inverse matrix. So if you've got 1, 0, 2, 0, 2, 0, 1, 0, 1, and the question is telling you that that matrix acting on the vector ABC gives you the vector minus 3, 4, 2. And what I'm saying is you could do the inverse matrix of this and multiply that here to cancel it out and multiply it on the left of this vector. and that would give you the answer A, B, C. But if you just go ahead and do this multiplication, A plus 0 plus 2C, A plus 2C must equal minus 3. And then the next element, 0 plus 2B plus 0 must equal 4. That's even easier. The last one, A plus 0 plus C must equal 2. And I'm sure that you can see this could become quite complicated. You might get 3 simultaneous equations, each with 3 variables. But in this case, it becomes quite easy. B must be 2. And comparing the first and the third equation, you can see that C must be minus 5, which means A must be 7. And we've answered it fairly quickly without too much work, and certainly with less work than finding the inverse matrix of T. But whichever method is easier for a given question, simultaneous equations or the inverse matrix are your 2 options. And you can practice both of those ideas using exercise 6e. And maybe I'll see you in the next video for eigenvectors and eigenvalues.